Hey, this is Math 6, Unit 6, Lesson 3, Staying in Balance. So first of all, we're going to begin with a little picture here. And I'm going to just pull it out of my teacher's guide so we can take a look at it. And so we have this picture of some socks. And we have a couple here, a couple there. These ones are supposed to be kind of pink, maybe hard to see in your picture. I'm not sure what color comes out on your monitor, and a couple blue ones there. So spend a few minutes in your class here just talking about what you notice and what do you wonder with these two hangers of socks. Okay? So if you need to pause the video for that and have a conversation, that's good. Okay. Alright, so things you might have noticed. You might have seen that, well, they each have two socks on them, right? Got two pink, two blue. You notice that perhaps that this one seems to be balanced and this one is not balanced, right? For some reason, this sock is hanging down further than that one, meaning it must be heavier than that one. If it would, maybe. It seems strange to have socks that look the same but one weighs more. Maybe you're wondering if there's something inside that sock. Maybe someone put some rocks or a marble in there or something. Hard to say. But this one's definitely balanced, and this one is what we would call unbalanced there. And that's really what we're going to be talking about today in our lesson, which is something you talked about, I believe, last year as well in one of your other classes. So here we go. So first of all, we have a couple diagrams here, A and B, with triangles and squares, triangles and squares. Alright, and we have some questions that they're going to want us to talk about, things that must be true, could be true or false, and cannot possibly be true about both of them. But a few things we notice is that, first of all, with A is definitely an example of something that is unbalanced, right? Because it's at that angle. It's not leveled out. Whereas the B one is certainly balanced. So things are equal there. And this is important because this is going to tie into what we talk about later with equations, because we're talking about solving equations. So if I have something like an equal sign, I know that 1 equals 1. That's going to be balanced, right? But if I was to add a 2 over here, now I'm not balanced anymore, am I? This one's going to be a little bit more than that side. So I would need to put a 2 over here in order to make that balance. So what I do to one side of the hanger, I have to do to the other side to make sure it's balanced. Just like what I do to one side of the equation, I have to do to the other side to make sure that it stays balanced. That's what's really important here in our lesson today. Okay? So when I take a look at these pictures, I can see from diagram A, one thing that must be true is the triangle must be heavier than the square. Another thing that must be true is a square must be lighter or be less than the triangle. Okay, that's something you could say there. For one thing that could be true or false, in terms of what could be, we could say that the triangle could have a value of 3 and the square could have a value of 1. That could be true, but it could be false. It could also be 4 and 2. It doesn't tell us what the value is going to be, but it could be. That's a could be kind of question. And one thing that cannot possibly be true is we would definitely say that the triangle is not less of a value than the square. Okay, makes sense? That's not possible. For B, a little different scenario here because we can see that this triangle, this one triangle, seems to balance out these 3 squares, just like that. So one thing that must be true is that one triangle is equal to 3 squares. That's a must be true because we can see it's being balanced there. In terms of what could be true or could be false, a triangle could have a value of 3 and a square could have a value of 1. But there are other things that it could have. For example, this triangle could have a value of 6. Now if that had a value of 6, we'll look at this later, that would mean each square would have a value of 2. Right? Because a 2 and a 2 and a 2 would combine to make a 6, so that would make that a true statement. So this is why it's a could be, because there's other things it could be as well. Things that cannot possibly be true would be maybe that the triangle is more than a triangle has has a less weight than one square. Something like that. I don't know. So think through what it could be or may not be, just an idea. Alright, let's look at the next section. It says to match equations and hangers. Alright, So in this little example here, we have 4 different diagrams of hangers. And we can see that they have some what we call variables when you have letters. These X's, we have a Y, we have Z's, we have a W, and we have values here for these squares, values of 1. Now all the values, one thing I noticed was that they all had, in this case, there are 6 right here. And this has a length of 6, this has a 6, and this one has a value of 6 right there. Over here, I can see that I have 3 different X's, right? So when I have 3 X's, that's like saying that I have 3 X's, right? I have 3 groups of an X. I don't know what X is, but I have 3 groups of an X. Over here, I have 1, 2, 3 again, so I know I have a 3, but then I have 1 Y. Now, I can think of this, don't get confused here, I have 1 group of Y, so if I want to think about that as being multiplying there, but this Y is just being combined with that, which means I'm just adding on to that one, okay? Over here, I can see just like the X's, I have 3 groups of Z's, or 3Z. And over on this side, I have 1 already, and I'm adding onto it 1 of the W's, whatever the W value is going to be. Because these are all hangers that are balanced, I can set them equal to each other like so. And then I end up with, I'm going to erase this 1 so it doesn't get confused here. So I end up with some equations like 3x equals 6, y plus 3 equals 6, 6 equals 3z, and 6 equals 1 plus w. Now I want you to match each equation to the ones down here. So which one shows a number plus 3 equals 6? Well, that's going to be this one right here. So that's going to be the one that uses the y. 3 times the number equals 6. That's this one. 3 times x equals 6. 6 equals 1 plus w. So we can do w plus 1. And it's nice to show that there because the order that you write the addition numbers in doesn't really matter. And this one will be the last one, 6 equals 3 times z. Again, interesting to note that these two are essentially exactly the same, aren't they? Different variables, but the same idea. It's 3 times some number equals 6, and this is 3 times some number equals 6. And so even though the 6 is on the right side or 6 on the left side, it's still balanced nonetheless, right? And so this goes with equation B, equation A, equation D, and equation C. All right? Now, it does also then say, in the next question here, find a solution to each equation and use the hangers to explain how you know what it means. So now I want to find a solution to each of these. So I'm going to come back here and find a solution and figure out, well, what is the value of x? What number times 3 can get you to 6? And so if you use the hanger, what you notice here is that I have 3 here and I have 6 here, meaning that for every 1x, I can use 2 of those, right? So I have 1 goes with 2, and 1 to 2, and 1 to 2, meaning that for every x, it equals 2. Over here, we can see in this case here, the ones, because of the same on both sides, I can basically subtract 3 of these, and if I subtract 3 of these, to keep it balanced, I subtract 3 of these, and that tells me that the y has a value of 3. This one's the same as we did in A. I know that the z goes with 2 of those, this z goes with 2 of those, and this z goes with 2 of those. So for every z, in this case here, we could say 2 equals z. And finally, on the last one, I can subtract 1, which means that w is equal to 1, 2, 3, 4, 5. 5 equals w. Okay, so now we have a solution there. And we can see how that works with the hangers there. You can also see how it works in terms of the equation. Take this one for example. If we take 6 equals 1 plus w, alright, what do we do over here? We subtracted a 1 from both sides. 6 minus 1 is 5, 1 minus 1 is 0, still equal to not to equal, and so we're left with the w, right? And this one here, the same idea. What do we do to both sides? We subtracted 3, and so that y equaled 3. Now when you look at these guys, when you have 3x equals 6, what we did is we divided these into segments of 2, didn't we? We divided it up. So it's the same as saying we're going to divide both sides by 3. So that x equals 6 divided by 3 is 2. And that's the same thing for this one here, just going on the other side. Alright, so that's the idea with the equations and hangers and keeping them balanced. Okay, so lots on that one, I know. That's kind of your big intro piece. Here are some balance hangers, and each piece is labeled with its weight for 3.3. It says for each diagram, write an equation, explain how to reason to find the weight of the letter, and then explain with the equation. Okay, so for A, let's look at A first of all. On the A side, we first have an x and a 3 that are going to be equal to an 8. Alright, now we don't have groups of x or groups of 3, we just have one of each. So we're going to write that as an x plus 3 equals 8, like so. Now, just to reason with this, what that means is that if I had 3, if I took away 3 from here, and I took away 3 from here, I'd be left with 5, right? So if I took away 3 from there, I'd be left with 5 over here. So I can think about chopping this up maybe, you know. You could think about it like that. You could think about taking this 8 and breaking up into 8 sections, 1, 2, 3, 4, 5, 6, 7, 8, and removing 3, 1, 2, 3, so you're left with 1, 2, 3, 4, 5. So that when you subtract 3 from both sides, x is equal to what remains, which is the 5. Let's look at B. For B, we have 12 on one side, and that equals, these are the same, 2 groups of y. When it's 2 groups of y, that's 2 times y. And now for this one, what are we going to do? Well, if I have 2 groups of y, that means this is 2 times, or y is twice the size of that. So I want to divide this in half, don't I? I want to take half of that. Well, how do I divide it by half? I divide it both sides by 2. So half of 12 is 6, and so y equals 6, right? Because this is 2 times as much, right? I'm going to make this half of that. Okay, now when you get to C, that's when it starts getting a little funnier, because now I have an 11, and it's equal to 4 groups of z. Which means it's like I need to take this z, this is 4 times as much as the 11. So if I take the 11 and break it into 4 sections, that's going to be the value of each z. Alright? So each z is 11 divided into 4 sections, because that's all we're doing. So how do you get 11 divided by 4 sections? Well, you divide both sides by 4, and you end up with 11/4 equals z. And that might seem a little strange, but that is actually the right solution there. You could write that as a mixed number. 4 times 2 is 8, and then 11 minus 8 is 3. So you're left with, 2. 4 times 2 is 8, so we use the 2. So 2 and 3/4 is the value of each of those. So these little segments here would have a value actually of 2 and 3/4. Like so. Okay, if you're not sure about that, let's add them up. 2, 4, 6, 8 there, and 3/4 plus 3/4 is 1.5, and another 1.5. So 1.5 is 3, and 8 plus 3 is 11. Alright, and finally D, which has some fraction numbers, but don't get too scared here. Again, we don't have any groups of anything, so what we have is we have 13 and 4/5 being equal to the W plus 3 and 4/5, right? These are just combined together to get that. So what are we going to want to do? We're going to want to take away 3 and 4/5 from both sides. So I subtract 3 and 4/5 from here, subtract 3 and 4/5 from here. The 4/5 minus 4/5 doesn't exist. 13 minus 3 is 10, and so 10 equals W, or W equals 10. Alright, so 4 different equations, all very similar. Sometimes you get whole number answers, sometimes you get fraction answers or decimals, and that's okay as well. So don't worry about getting a kind of number that's not a whole number all the time. Alright, let's take a look at our summary for today before we jump into our homework. Basically, the summary here, looking at it, it says a hanger stays balanced when the weights on both sides are equal. So balance means that they're going to be equal. We can change the weights and the hanger will stay balanced as long as both sides are changed the same. This is a key thing here. We can change the weights and the hanger will stay balanced as long as both sides are changed in the same way. Right? This is how an equation works. The same way it works the same as balancing a hanger. So if we add 1 to one side, we have to add 1 to the other. If we divide by 3 on one side, we divide by 3 on the other. And in doing so, you end up with a balanced equation all the way through. And that really was what the lesson was about today. Okay, so I'm going to pause there and let you work on your homework, then we'll come back together and check it out. Alright, here we go, homework check time. Let's select all the equations that represent the hanger. Alright, so in this hanger here, we have 3 groups of x, so we could write that out as 3x, and that's equal to, in this case here, 1, 2, 3, 4, 5, 6 of something, right? That's the basics way we write it from our lesson part here. So what does this match up here? Well, in this case here we see an x, an x, and an x. That is 3 groups of x technically, that's okay. And here we have 1, 2, 3, 4, 5, 6, and that's the same as the other side, so that would work, right? If these were all 1s, that is 3 x's equals 6 1s. That looks just fine. Yes, it doesn't match that, but it's the same idea. Over here we have 3 groups. Well, this is not 3 groups, right? This is x times x times x. So that's a little different. That's x. That is not 3 times x. To say that x times x times x is the same as 3x doesn't work out too well. Okay, let's pretend that x had a value of, let's just use 2. Okay, so what is 2 times 2 times 2? 2 times 2 is 4, times 2 is 8. But if I put a 2 here, what's 3 times 3? 3 times 2 is 6. That doesn't work. So x times x times x is not the same as 3x. So keep that in mind. This is not a true statement. But this one we already know is. That's going to work. Over here, this is x plus 3. Well, that's not x plus 3. That's going to be 3 times x, so that's a no. And again, this one, same idea. X, x, and x is not the same as 3x, so that's a no as well. So just A and C. Number 2. Write an equation to represent each hanger. Alright, so in this case here, we have how many groups of x? We have 2 groups of x. And what does it equal? 1, 2, 3. Alright, here we see there aren't any groups. We just have a combination of 2 things. We have a W being added together with a 1.3, and it's equal to, what's on this side? 2.7. On this one we see we have 3 groups of y, so we can write 3 times y, and that's equal to this side, which is 5.1. Here, no groups, just 2 things combined together, so z plus a third equals, on this side over here, a half. Doesn't ask you to solve it, just wants you to set up the equation. For the 3, write an equation to represent the hanger and explain how to reason with the hanger to find the value of x and explain with the equation. Alright, so here we go. For this equation, we can see that we have 2 groups of x equal to 14.62. Okay, so as you explain with your words, you're going to write some stuff down here. What we're going to see is that because this is 2 times the size of that makes the 14.6, and x is going to be equal to half of the 14.6 because the 2 times the x gets you to there. Okay, so to solve this here with this equation, we would divide both sides by 2 to show that x is equal to 7.31. And you could use a calculator for that. I actually didn't use a calculator because this is an even number. Half of 14 is 7. Half of 3 is, 6 is 3. And half of 2 is 1. Because they were all even digits there, you could just do some mental math. Alright, number 4. It says, Andre says that x is 7 because he can move 2 1s and with the x to the other side. Okay, look at the picture. So x is 7 because he can move 2 1s with the x to the other side. So here's our picture. Andre says he can just take these two guys here and just move them over there to make it go 1, 2, to make x equal to 1, 2, 3, 4, 5, 6, 7. He says that is 7, and so x equals 7. That's what Andre says. Well, the question is, do you agree with Andre? That's the question here. Can you just take 2 off of one side and move them over and it stays balanced? Right now it is balanced. So if we take 2 away from here and put them there, will this still stay balanced and level? I would say no. We would disagree with Andre. And the reason is that whatever you do to one side, you have to do to the other side. So if I can't just take some from away and put them there, now I'm going to have a unbalanced, right? So explain your reasoning with your words for why that's not going to work. Now, if we took it away, and we took away 2, and we took away 2, then we'd have a different result, wouldn't we? We would say that x equals what? X would be equal to what remains over there, 3. That's a better solution, but that's not what he got. Number 5, match these equations in one of the diagrams. Okay, so here 12 minus m equals 4, 12 equals 4 times m minus 4 equals 12, and m divided by 4 equals 12. Alright, so let's see what we have here. So in this case, we look at our big number. Our big number is what it's basically going to be equal to at some level. Okay, so this m, the long rectangle, is equal to the combination of 12 and 4. 12 plus 4. Now, when we look over here, I don't see 12 plus 4 equals m anywhere, right? I don't see that anywhere. But what I do see is I see 12 minus m equals 4, or m minus 4 equals 12. I see both of those. So the question is, what is that going to go with? Well, let's see. If we were to subtract 4 from both sides, what would we have? We would have m minus 4 equals 12. And that one we do see right here. That's C. Okay, so I don't know how you want to write this here. This goes with C. For this one, what we see is we have 12 equals 4 plus m. Now again, I don't see 12 equals 4 plus m anywhere. We have already used that one. We know it's not those two because of multiplication. So how did they get to A? Because it is definitely A. This one says that we're going to have 4 is what we're equal to. How do we get the 4 there? Well, we subtract m from both sides. So we have 12 minus m equals the 4, and that is A. So again, set it up the way you want to set it up, and then move things around by doing it to the same size, subtracting m from both sides, or subtracting 4, so you can get the value they're looking for, or in that kind of order. This one, we have m is equal to 1, 2, 3, 4, 4 groups of 12. So 4 groups of 12. Now again, do you see m equal 4 times 12? Nope, I don't. I see 12 equals 4 times m, and I see 12 equals m divided by 4. So we want to get the 12 by itself for both of these equations. So in this case here, to get the 12 by itself, let's divide both sides by 4. And now we're left with m divided by 4 equals 12, right? Because those cancel out, and that matches choice D. And we'll do the same thing over here. This one we start by saying that 12 equals 4 groups of m. And so that one is our easiest one actually. It's the one that actually works the most. 12 equals 4m. No change to be made, and B. So that was the easiest one of all of them. Alright, number 6. It says the area of a rectangle is 14 square units, has a side length of A and B. Given the following values of A, find B. Okay, so the area of a rectangle is found by doing what? Multiplying A times B is going to equal 14. And what they're giving us every time is they're giving us the value of A, so we can find the value of B. So it looks like this for number 1. We have A times B equals 14. A is 2 1/3 times B equals 14. And now we have to solve that out. So let's do this. 3 times 2 is 6, plus 1 is 7. So what I have is 7/3 times B equals 14. How do I get the B by itself? I multiply this one by the reciprocal, but I do it to both sides of the equation. So the 3's cancel, the 7's cancel. I'm left with B over here. And what is B going to be equal to? Well, this can reduce. 7 goes into 14 2 times. 2 times 3 is 6. And we solve it just like that. Okay? We're going to do the same thing for numbers 2 and 3, right? So A is 4 1/5 times B equals 14. 5 times 4 is 20, plus 1 is 21/5 times B equals 14. We'll multiply both sides by the reciprocal. So the 5's cancel, 21's cancel, and then B is going to be equal to whatever's left over here. 7 goes in here 2 times, 7 goes in here 3 times, 2 times 5 is 10, and this is on the bottom still just a 3. So I got 10 over 3, or I could say 3 1/3. And finally the last one, 7/6 times B equals 14. I'll multiply both sides by the reciprocal. So those cancel, leaving B equal to 7 goes in here 1 time, 7 goes in here 2 times, and 2 times 6 is 12. Alright, so we have our values of B right there. Okay, and finally number 7. Lending to save up $20 for a game. How much money does she have if she has saved the following percentages of her goal? Alright, 25%, 75%, and 125%. We can do it with just some math, or we can do it with a tape diagram as well. Let's show you a quick tape diagram just so we can do that while we're thinking about it. So here's how a tape diagram works once again. If this is the dollar amount and this is the percent, and we know that the goal is $20 and that's 100%, then we could use that to say, well, I know that 50% is half, so half of 20 is 10. 25% is half of 50, so what's half of 10? 5. 75 is what I get when I add 25 and 50 together, so 5 plus 10 is 15. And then I could say, well, in this case, I need to find 25, 75. Well, 25 is right here. 25 is going to be $5. 75 is going to be $15. 125 is what I get when I add 100 and 25 together. So 100 is 20 and 25 is 5. And Stevie G is awake this morning, nice and early. Hop down there, buddy. The kids need to see what's going on. The last question. Alright, so we're going to combine 100 and a 5 to get 25 for what 125 is like. Can you do it a different way? Sure you can. 25% of $20 is like doing 0.25 times 20. 75% is 0.75 times 20. 125 is 1.25 times 20. And by doing that, you'll end up with the same solutions. I just want to show you the tape diagram once again, since we don't do this all the time, just to remind you how that works. That's it for today. Have a great day, and we will see you next time.